All right, let's jump straight into a really core concept in radiation biology,
Right.
something that has huge implications for how we think about treating cancer. We're talking about the oxygen effect and the oxygen enhancement ratio, or OER.
Exactly.
And this isn't just, textbook theory. Understanding how oxygen changes radiation's punch is absolutely key for making smart clinical decisions.
Absolutely, Q. We've talked before about how the type of radiation, its LET, shapes its impact.
Right.
Now we're tackling another major player, especially for those workhorse radiations like X-rays and gamma rays, basically, whether oxygen is present or not.
Right.
Think of it as understanding radiation's molecular allies and enemies, you could say.
Okay, so let's unpack the oxygen effect itself. What's
Right.
the basic observation here?
Well, at its heart, the oxygen effect is this. Mammalian cells are just significantly more vulnerable to damage from those low LET radiations, standard clinical X-rays, gamma rays, when they're surrounded by molecular oxygen.
Hmm.
We call those conditions oxic or aerated. But flip that scenario. When the same cells are in a low oxygen state, anoxic or hypoxic, they actually become tougher, more resistant to radiation's effects.
That sounds like a really fundamental difference. It's almost like the radiation needs oxygen's help to do its job properly.
Exactly. A simple analogy, maybe. Think about trying to burn something. It burns much better with a good supply of oxygen, right?
Sure. Yeah.
It's sort of similar here. Oxygen seems to, well, amplify the destructive potential of radiation within the cell. And this difference, based purely on oxygen levels, has huge consequences when we think about tumors, which often have these poorly oxygenated pockets.
So oxygen makes cells easier to zap,
Mhm.
essentially. How do we actually quantify that difference? That's where the OER, the oxygen enhancement ratio, comes in.
It does, yeah. The OER is our way of putting a number on just how much oxygen boosts radiation's effectiveness. It's defined as the ratio of the radiation dose you'd need under hypoxic conditions to get a specific biological effect. Let's say killing 50% of the cells, compared to the dose you'd need under oxygen-rich, oxic conditions to get the exact same biological effect.
Okay, could you break that down a bit more? What's the actual formula?
Sure. The equation itself is pretty straightforward. OER equals the dose required under hypoxic conditions divided by the dose required under oxic conditions. And the key is it's for the same level of biological effect, like the same amount of cell kill.
Got it. So it's a ratio of doses needed.
Exactly, doses.
So a higher OER means you need a lot more dose when oxygen is low, which tells you hypoxia is really protective.
That's it.
What are the sort of key takeaways about this OER value?
Okay, several crucial points. First, like you said, it's a ratio of radiation doses. Second, it tells us exactly how much more radiation we need to pile on to oxygen-starved cells to get the same result as in well-oxygenated tissue.
Right.
And for the low LET radiation, we typically use photons, the OER, at doses that matter clinically, usually falls somewhere between 2.5 and 3.5.
Mm. 2.5 to 3.5.
Yeah, think about that. Hypoxic cells can be up to 3.5 times more resistant. It's significant.
Huge.
And finally, a fundamental point. The OER is never less than 1, because lacking oxygen never, ever makes cells more sensitive than when oxygen is present. Hypoxia is always protective, at least to some degree.
That difference needing potentially 3 times the dose that really hits home the clinical challenge. How can we visualize this OER thing? I think I remember seeing graphs.
Yeah, you're probably thinking of cell survival curves.
Yeah.
Imagine plotting, say, the a log of the surviving fraction of cells against the radiation dose.
Okay.
You'd have one curve for cells that are fully oxygenated and another for cells that are hypoxic. Both curves will obviously slope downwards, more dose, fewer survivors.
Mm-hmm.
Now, the OER at a specific survival level, let's take, say, 10% survival or SF equals 0.1, is found by looking at the horizontal distance between those two curves at that 10% line. The hypoxic curve will be shifted way over to the right, meaning you needed a much higher dose to kill the same fraction of cells compared to the oxic curve. The ratio of those two doses on the horizontal axis is the OER for that survival level.
Okay, yeah, that visual makes the dose difference really concrete. So we know oxygen boosts radiation's effect, OER measures it, but what's the actual mechanism? The nitty-gritty molecular reason why? Let's get into the oxygen fixation hypothesis.
Great question. Yeah, the oxygen fixation hypothesis is really the cornerstone explanation for this. Remember that low LET radiation, like our X-rays, does most of its damage indirectly.
Right, through water molecules.
Exactly. The radiation ionizes water inside the cell, creating these highly reactive free radicals, especially the hydroxyl radical, the OH radical. These radicals are like molecular bullets. They zip around and damage critical targets, especially DNA, creating damage sites. We can call a damaged DNA site a DNA radical, maybe R radical for short.
Okay.
Now, direct interaction of radiation with DNA also creates these R radicals, but it's less dominant with low LET.
So we've got these damaged DNA sites, these R radicals. What happens to them if there's no oxygen around in that hypoxic state?
Okay, under hypoxic conditions, these DNA radicals, R radical, are chemically unstable. But importantly, they can be repaired by naturally occurring molecules in the cell, like a rapid response repair crew. Key members of this crew are compounds containing sulfhydryl groups, SH groups. Glutathione is a really important one. So without oxygen, R radical can react with one of these SH compounds, and basically the damage gets chemically restored. It becomes RH repaired DNA. The lesion is gone.
But if oxygen is there, the repair crew gets elbowed out.
Pretty much, yeah. Molecular oxygen O2 is also highly reactive. It's electronegative, and it competes for that R radical site. When oxygen is present, it reacts very rapidly with the R radical, often before those SH repair compounds can even get there. This reaction forms a different kind of radical, an organic peroxyl radical, RO2 radical. And this is the fixation part. This RO2 radical form of damage is much more stable chemically, and it's way less likely to be easily repaired by the cell's normal enzymatic repair pathways. It essentially makes the damage permanent, or at least much harder to fix, leading to lethal consequences.
So oxygen changes the outcome of that initial radical hit. It goes from potentially fixable to, well, fixed in a bad way, locked in.
Locked in is a good way to put it, yeah. More permanent, more lethal damage per unit of dose.
And the timing must be absolutely critical here, right? These radicals, they don't stick around for long.
Not at all. You're talking microseconds, maybe milliseconds, extremely short-lived. So for oxygen to effectively intercept that R radical and fix the damage, it has to be present right during the radiation pulse or within milliseconds right after. If you add oxygen even, say, a second later, it's largely too late. The initial radical chemistry has already happened. Those R radicals have either been repaired by SH groups or undergone other reactions. The sensitizing effect is dramatically reduced. It's a really tight time window.
Now, we focused on the big impact with low LET radiation, but I recall the OER isn't always that 2.5 to 3.5 number. It depends on the radiation type itself. How does linear energy transfer, LET, play into this?
That's a really crucial point. Yes, the OER's magnitude is strongly dependent on LET. As we've established, low LET radiation X-rays, gamma rays, causes damage mostly indirectly, creating those radicals that oxygen can then fix. So high OER, that 2.5 to 3.5 range.
Right, because the mechanism relies on those radicals.
Yeah.
But what if the radiation hits harder, more directly? Like high LET.
Exactly. When you switch to high LET radiation, think alpha particles or neutrons, the OER plummets. For alpha particles, it actually approaches 1.0.
Wow, basically no oxygen effect at all.
Pretty much. For neutrons, it's maybe around 1.6, still much lower than for photons. And the reason is that high LET radiation causes damage primarily through direct action on the DNA. It deposits energy so densely that it creates these complex, clustered lesions, think multiple double-strand breaks right next to each other.
Nasty stuff.
Very nasty. And these are inherently difficult, sometimes impossible, for the cell to repair correctly, whether oxygen is there or not. The initial damage is so severe that the whole oxygen fixation pathway becomes much less relevant.
So it's like an inverse relationship then. Higher LET means lower OER.
Precisely.
That makes sense. The damage is bad enough on its own. Oxygen doesn't add much more lethality, relatively speaking. I remember there's a point where LET is most biologically damaging overall.
You do. The sharpest drop in OER actually happens around an LET value of about 100 keV per micrometer. And interestingly, that's right around the LET value where the relative biological effectiveness, the RBE, tends to peak. So high LET is more damaging per gray, and that damage is less dependent on oxygen.
Okay, so LET is a big factor.
Yeah.
What about the actual amount of oxygen present? Is it just, the more oxygen, the higher the sensitivity in a straight line?
No, actually, it's not that simple. The relationship between radiosensitivity and oxygen concentration is quite nonlinear. It's pretty fascinating. What you see is as you increase the oxygen level from absolutely zero anoxia up to just very low levels, there's a really sharp, steep increase in radiosensitivity.
Really?
Yeah, in fact, you get about half of the maximum possible oxygen sensitization effect at an oxygen tension of only about 3 millimeters of mercury.
3 millimeters. That's tiny. That's like, what, 0.5% oxygen?
Exactly, around 0.5%. So even a tiny whiff of oxygen makes a huge difference compared to none at all.
Wow. Okay, so it jumps up quickly. What happens as you keep adding more oxygen? Does it keep going up just as fast?
No, that's the thing. After that initial steep rise, the curve starts to flatten out. The radiosensitizing effect begins to plateau. By the time you reach oxygen tensions of around, say, 20 to 40 millimeters of mercury, you're pretty much near the maximal sensitization you're going to get from oxygen.
In that 20-40 range, that sounds familiar from physiology.
It should, because that range, 20 to 40 millimeters of mercury and above, is typical for the oxygen levels found in most of our normal, healthy tissues. Even venous blood is usually in that range or higher.
Okay, so our normal tissues are already sitting on that plateau part of the curve. They're already pretty much maxed out in terms of oxygen-related radiosensitivity.
Exactly. Adding more oxygen systemically, like breathing pure oxygen at normal pressure, probably isn't going to make healthy tissues significantly more sensitive to radiation.
But what about those tumors, the hypoxic ones?
Ah, that's the critical difference. Many solid tumors, especially as they grow larger, develop regions where the oxygen supply is poor. The oxygen tension in these areas can fall well below that critical 3 millimeters of mercury level.
So they're down on the steep part of the curve.
Precisely. They're sitting in that zone where even a small increase in oxygen could cause a big jump in radiosensitivity.
Right.
And this is the whole basis for therapies like using hyperbaric oxygen, trying to force more oxygen into those starved tumor regions to push them up that sensitivity curve and make the radiation more effective there. This difference in oxygenation, normal tissues, usually well oxygenated, 20-40 millimeter Hg. Tumor regions, often very poorly oxygenated, 3 millimeter Hg, presents a major therapeutic challenge. It's why hypoxia is such a big deal in radiotherapy.
That really sets the clinical relevance perfectly. Let's talk about some clinical pearls then. What are the absolute key takeaways regarding oxygen effect in OER for clinical practice?
Okay, clinical pearl number 1. Hypoxic tumor cells are significantly more resistant. Remember that factor of 2.5 to 3.5 times to our standard low LET radiation. This resistance is a major cause of treatment failure and local recurrence.
Got it. Pearl 1, hypoxia equals resistance, big time. Pearl number 2.
Clinical pearl number 2. Even very, very low levels of oxygen, think around that 3 millimeters of mercury mark or 0.5% O2, provide a substantial radiosensitizing effect compared to complete anoxia. It doesn't take much oxygen to start making a difference.
Right, that steep initial rise. Okay, and the third pearl.
Clinical pearl number 3. High LET radiation, like neutrons or alpha particles, is much less dependent on oxygen levels. Its OER is low. This means its effectiveness isn't compromised nearly as much in hypoxic environments, which could be an advantage for treating known hypoxic tumors.
Perfect. Those 3 pearls really nail the key concepts. So how does all this understanding, the effect, the OER, the mechanism, the LET dependence, how does it actually shape our clinical decision-making and treatment strategies? It must influence a lot.
Oh, absolutely. It underpins so many strategies we use or investigate. Take fractionation, for example, giving radiation in multiple small daily doses.
Yeah, standard practice.
Part of the rationale for fractionation is to allow for tumor reoxygenation between doses. As you kill the well-oxygenated cells in your blood vessels, the tumor might shrink a bit, allowing some of those previously hypoxic cells to get closer to the blood supply, become better oxygenated.
And therefore more sensitive to the next dose of radiation.
Exactly. It's trying to catch those resistant cells as they potentially become more vulnerable over the course of treatment.
And then there are drugs specifically designed to tackle hypoxia, right?
Yes, several classes. We have hypoxic cell radiosensitizers. The classic examples are nitroimidazoles like misonidazole. These are drugs that sort of mimic oxygen, electronically speaking. They get into hypoxic cells, and when radiation hits, they react with those DNA radicals to fix the damage, much like oxygen does.
Making the hypoxic cells act more like oxic cells.
Essentially, yes. Then there's another class, bioreductive drugs, or hypoxic cytotoxins. Tirapazamine is a well-studied example. These drugs are actually activated by the low oxygen environment. They get chemically changed into a toxic form only in hypoxic conditions, specifically killing those resistant cells.
That's clever, targeting the problem directly.
It is. And then, as we mentioned, there are the strategies aimed at increasing oxygen delivery itself.
Like hyperbaric oxygen.
Yes, putting patients in a high-pressure oxygen chamber during treatment. Also, carbogen breathing a mixture of oxygen and carbon dioxide, which can sometimes improve tumor blood flow and oxygenation. Improving hemoglobin levels to maximize oxygen carrying capacity is important too, though the direct clinical benefit in terms of overcoming hypoxia specifically is sometimes debated or complex.
And in select cases, we might even think about using different radiation beams altogether.
That's right, because high LET radiation neutrons, heavy ions like carbon, has that low OER, it's less reliant on oxygen. So, for tumors strongly suspected to be very hypoxic, using these particle therapies might offer a way to bypass the oxygen problem.
Lastly, are we getting any better at actually seeing where the hypoxia is within a tumor?
We are. That's the field of hypoxia imaging. Techniques like PET scans using specific tracers like F-MISO, fluoromethanidazole, can bind preferentially in low oxygen regions.
So you could potentially get a map of hypoxia in the patient's tumor.
That's the goal, to identify these resistant areas before or during treatment. The hope is this could allow for, say, dose painting, selectively boosting the radiation dose just to those hypoxic spots, or choosing patients who might benefit most from hypoxia-modifying drugs or high LEP therapy. It's an active area of research.
Okay, fantastic overview. Let's switch gears slightly and do a quick board blitz, solidify some of these key facts. Ready?
Let's do it. Fire away.
Question 1. The Oxygen Enhancement Ratio, OER, for low linear energy transfer, LET radiation, is typically in which range? A, 0.5 to 1.0, B, 1.0 to 1.5, C, 1.5 to 2.0, D, 2.5 to 3.5.
That would be D, 2.5 to 3.5. That's the Classen range for photons at higher doses.
Correct. Question 2. According to the oxygen fixation hypothesis, molecular oxygen enhances radiation damage primarily by doing what? A, increasing the number of initial DNA radicals formed. B, directly causing double-strand breaks in DNA-C, inhibiting enzymes involved in DNA repair. D, reacting with DNA radicals to prevent their chemical repair.
Okay, the key word is fixation. So it's D, reacting with the DNA radicals to form that peroxyl radical, preventing repair by things like glutathione.
Exactly. Question 3. Which type of radiation would you expect to have the lowest oxygen enhancement ratio? A, cobalt-60 gamma rays. B, 6 mega-electron volts X-rays. C, fast neutrons. D, alpha particles.
Lowest OER means highest LET, least dependent on oxygen. It's got to be D, alpha particles. Their ODR is close to 1.
Perfect. Last one, question 4. The radiosensitivity of mammalian cells increases most steeply with increasing oxygen tension over which range? A, 0 to 3 millimeters of mercury. B, 10 to 30 millimeters of mercury. C, 40 to 100 millimeters of mercury. D, 100 to 760 millimeters of mercury.
The steepest part is right at the beginning, at very low oxygen levels. So that's A, 0 to 3 millimeters of mercury.
Excellent. Okay, so just to wrap up this deep dive then, the big takeaways are oxygen is a huge radiosensitizer for the low LET radiation we commonly use.
Right. And its absence, hypoxia, causes significant radioresistance. We measure this with the OER, typically 2.5 to 3.5 for X-rays.
And the mechanism is thought to be the oxygen fixation hypothesis, oxygen reacting with DNA radicals, making the damage permanent and harder to repair.
We also covered that OER goes down as LET goes up, and that the oxygen effect is most sensitive, that steep part of the curve, at very low oxygen concentrations, below about 3 millimeters of mercury.
And clinically, tumor hypoxia is a major barrier to successful radiotherapy, driving the development of all these strategies we discussed: fractionation, sensitizers, cytotoxins, hyperbaric oxygen, high LET, hypoxia imaging.
It really highlights how fundamental this radiobiology is to improving treatment.
Absolutely. So maybe a final thought to leave everyone with. Given everything we know now about the oxygen effect, and with technology constantly advancing, what breakthroughs might be on the horizon? What future strategies could really crack this problem of hypoxic resistance?
That's the multi-million-dollar question, isn't it? Maybe more sophisticated imaging, guiding truly personalized hypoxia targeting, or perhaps novel drugs that work even better than current sensitizers, or even ways to manipulate the tumor microenvironment itself. Lots to think about.
Definitely food for thought. Well, this has been a fantastic deep dive into the oxygen effect and OER. Thanks for walking us through it.
My pleasure. It's a crucial topic.
And for everyone listening, remember you can find more resources and practice questions over at radonsmartlearn.com. Be sure to subscribe to Radon Smart Review for our next deep dive. Thanks for tuning in.